This is problem 9-18E. It's on page 515. A wood joist in a commercial building is 14 foot 6 inches long and carries a uniformly distributed load of 50 pounds per foot. Let's start sketching this because there's no figure. So here's the joist that has a length of 14.5 feet and has a uniformly distributed load. What did they say? 50 pounds per foot. Okay, let's see. Cross section, it is 1.5 inches wide. So that's just like a 2x4 basically on the side. And 9.25 inches high. Anybody know what a 9.25 inch high beam is normally called? What is this normally called? 2x10, that's right. You go down to Lowe's or Home Depot, that's a 2x10. Why is it 2x10? 1.5. It was. It used to be before they started shaving them off and making them smooth. That's right. So anyway, so that's what you actually get when you buy a 2x10. All right, let's see. If it is made of southern pine, compute the maximum deflection of the joist. Now, they didn't really specify how it's supported, so I'm going to assume that it's just simply supported at either end. I think that was their intention, but they didn't make that particularly clear. Let's see, southern pine, compute the maximum deflection, we can do that. Also compute the stress in the joist due to bending and horizontal shear and compare them with the allowable stresses for number 2 grade southern pine. So, what does that mean? Well, we're going to need the moment of inertia, so let's go ahead and get it. The moment of inertia would be 1/12 BH cubed, so that's going to be the base, 1.5 inches, multiplied by the height, 9.25 inches, quantity cubed over 12. You all know that. This is simple by now, right? Easy stuff. So 9.25 cubed times 1.5 divided by 12. Let me just get rid of this and write down the result. It's 98.9316 or so inches to the fourth. Okay, so there's our cross-sectional property that we need. Now, the other thing we're going to need is Q. So let's just go ahead and write that down as well. Q will be calculated. Let me ask you, where will the maximum shear stress be located? Not the maximum shear load, but the maximum shear stress. At the center, right? It's going to be at the center of this beam. So if we're interested in the shear at the center, then we need to take this as the particular area, right? And so if we're going to calculate Q, it would be the particular area multiplied by the distance from the centroid up to the center of that particular area. But that's pretty easy, right? You guys tell me, how far would it be from the neutral axis up to the centroid of that area?
2.31.
The quarter of this, right? Yeah, 2 point whatever. If it was a 2x10, it'd be 2.5 inches. Okay. So let's see. How about the area itself? Well, that's just going to be 9.25 inches over 2, right? For half the height multiplied by 1.5 inches. So there's our area. Y bar, you just told me, is 9.25 inches over 4. Okay. So that should give us Q. Whoops. I lost my calculator. Ever done that before? Okay, so that would give us Q for this beam. So let's see, 9.25 times 1.5 divided by 2, divided by 4 multiplied by 9.25. There we go. Again, well, you guys aren't familiar with Q yet. I'll leave that up there for a minute. So 16.0423. No, that's not right. 430, if I round it properly, inches cubed would be Q. Okay, so now we've got the area properties that we will need. Now we're supposed to find out the deflection and the stress. We can get the deflection pretty easily now that we've got I. All we have to do is go to the back of the book and look up the equations for deflection. So let's see. What case is this? Simply supported. Let's see. I've chosen a case. I think it's on page 735. What do you think? Which one? D. I agree. It would be case D. all right? Do we care about the fact that case D has a little bit of overhang? No, it doesn't matter. We don't in our problem. Everything else will be the same. All right, so let's calculate the deflection at B. They call B the center, and they note that that's where they note that's where the maximum deflection would occur, which it makes sense intuitively, right? That's pretty obvious. So anyway, the deflection at B would be -5 lowercase w. You have to be careful. When we talk about distributed loads, usually the distributed load itself is given the symbol lowercase w. I usually put a little arm on it to indicate that that's a small letter. V's and W's can be difficult, so I put an arm on it. But capital W is the resultant of that load. Okay, so if you notice in D, at the top in the figure it says the total load, capital W, is lowercase w times the length, which makes sense. Anyway, we're going for that, but we're going to go ahead and, hang on. Oh, yeah. We're going to go ahead and plug it in this way, and they have another equation. I'll write them both down in a minute, 384 EI. They have another equation like this, -5 capital W L cubed over 384 EI. You can see this is the same thing, right? Because this W is just lowercase w L, so that's where that comes from. You can plug it in any way you want. It doesn't matter too much. Okay, you get the same result. So let's just plug in the numbers and see what we get. So -5 times 50 pounds force per foot multiplied by L, which was 14.5 feet, but that has to be raised to the 4th power, over 384. We're going to need the elastic modulus. Let's go get it. We know this is southern pine. So material properties. Page 719 gives us the elastic modulus. This is grade 2, southern pine. Okay, let's see. It looks like 1300 KSI. We're in English units, so that's what we need to use. Okay, and then I, well, we calculated I earlier. That's 98.9316 inches to the 4th. Okay, again, we'll have to deal with units. What about the pound units? What should I do with that? I have to convert it one, because here I have thousands of pounds per square inch. In fact, let's write it that way. This is the same thing as 1,000 pound force. Yeah, let's make this clear. Per square inch. Okay, now I don't really have to do a conversion because I've plugged it in that way, right? That's 1,000 pounds per square inch. But now we've got the foot and inch problem, so let's take care of that. We'll multiply the top. We were looking at deflection. I'd like that in inches. So let's see, this is basically feet cubed. So 12 inches per 1 foot cubed will take care of the cubic feet. That'll all be gone. And let's see, what will we be left with? We've got inches cubed over inches squared. So that'll be just inches. So this works out. Okay. Plug in the numbers, see what we get. Notice how I always check the units before I plug in numbers. That's a really good habit for you to get into. If you don't have that habit yet, please develop it. It will help you in this class, and it will help you in all of my other classes. Well, except for probably controls, but it'll help you in all my other classes for the most part. Okay, so 5 times 50 times 14.5 to the 4th power times 12 to the 3rd power, divided by 384, divided by 1,300, divided by 1,000, don't forget the 1,000 from the conversion factor, divided by 98.9316. My calculator had to think for a second, but it came up with 0.3867 or so inches of deflection. Anyone else do this as well? Same number? Okay, so there's the deflection at the center of that beam. 0.386 inches. What's that closest to in fractions? It's about 3/8 of an inch. That's quite a bit of deflection. I mean, think about a 14.5-foot beam deflecting 3/8 of an inch. You should be able to see that. In fact, if you actually did that, I'd be worried about the beam buckling in the center, because you're deflecting it so much. If my arm represents the beams, the board sitting on its side, and you're applying a load to it that's so large, you're deflecting it so much at the top, I'd be worried about it potentially going out of plane. I don't know. That would be my first concern. I don't know that that would actually happen. What else did they want us to do? Let's find out. We're supposed to compute the stress in the joint in bending and horizontal shear and compare them with the allowable stresses. Well, how much is the shear? We don't know yet, right? We haven't made our shear and moment diagrams. So let's just make some notes of what we found so far. It's kind of like a trophy, right? You write down your answer, that's your reward for doing the work, right? Kind of excite you about this. So YB is about 0.3867 inches. We won't need any of these other details later. So let me put the shear and moment diagrams beneath this. Of course, it's going to be a pretty straightforward shear and moment diagram. See, I guess I need to go ahead and calculate the total load. So that would be equal to 50 pounds force per foot multiplied by 14.5 feet. So 14.5 times 50 gives me a total load of 725 pounds force, half of which is going to be over here, 362.5 pounds force, and the other half will be over here. Okay, so the initial shear in pounds force will be, let's see, if we cut the beam here, the shear is going to have to act downward. That's a positive thing. So it would be at 362.5. And of course, it would just decrease linearly, going through 0 at the center, down to 362 or negative 362.5 pounds force on the other end. And the moment diagram, which would be in foot pounds force, we'll start at a 0 moment on the left-hand side, and all we have to do is add up area. So it's going to add a lot of area initially and then level off. The slope is not discontinuous, and so we expect this to be smooth, so the tangent line up here is just a 0 line. That's what this says. And come back down to 0 because these two areas are the same. In fact, if we calculate this area, it'd be 362.5 multiplied by L over 2 and then divided by 2 because we're dealing with a triangle. So let's see, 362.5 multiplied by 14.5 over 2 and then divide by 2 to get the area of the triangle. Looks to me like the maximum moment is going to be 13, 14 or so foot-pounds force. I rounded off something after the decimal place, but that's close enough. Okay, so we're going to use a maximum shear of 362.5 pounds force and a maximum moment of 13, 14 foot-pounds force. Okay, there are the two loads. Notice that the shear load, or the shear stress, is going to end up being the most out at the ends, but the bending stress is going to be the greatest at the center. How much would the shear stress be at the center? 0. There's no shear load, right? So 0 at the center. Okay. Well, how do we do this? Well, let's see. You remember the equation for the bending moment? What is it? Anybody got it memorized? MC over I, if we want the maximum. Usually we have MY over I because we can talk about the stress at any cross section or any height. Okay. So this would be the height C, but we could go to any height Y that we wanted to and look at the bending stress. Okay, which of course is going to come out from the board. I can't actually draw something coming out from the board, but I can try to do it like that. Okay. By the way, did I draw this stress in the right direction? If this is the top of the beam? No, it'd be the other way, right? This would be a compressive stress, not a tensile stress. Now, the tensile stresses would end up being at the bottom. And of course, they'd be maximum at the very bottom and go to zero as you move toward the neutral axis and then have the opposite on the top. Okay. Anyway, so we know what M and I are, that's no problem. 13, 14 foot-pounds force. I, we know, is 98.9316 inches to the fourth. But what about C? What is C? We want to go all the way to the outer fiber, right? How far is it from the neutral axis to the outer fiber? Half of 9 1/4, right? So 9 1/4 inches, 9.25 inches over 2. Okay. Now let's see, we've got a small problem here because again we have feet to take care of. So there's 12 inches per 1 foot. That'll take care of the foot. And we should end up with PSI. In fact, we do. These two will cancel with 2 down here, and we'll be left with pounds force per square inch. So let's see, 13, 14 times 9 1/4 times 12 divided by 98.9316 divided by 2. Looks like the bending stress is 737.15 PSI. Okay. Anybody else second that? Agree, disagree? Okay. What about the shear stress? Well, the shear stress is VQ over IT. Well, we know the shear is 362.5 pounds force. Okay. Q is this geometry property we came up with, the 16.0430 inches cubed. And I is still 98.9316 inches to the fourth. And then T, the thickness. What is the thickness? Well, just 1.5 inches. All right, so again, let's see. Yeah, we'll end up with pounds force per square inch. So it looks like our units will work. That's a good thing. 362.5 times 16.043 divided by 98.9316 divided by 1.5. Okay, looks like the stress is 39.19 or so PSI. Now, before we go any farther with this, I want to ask you a couple of questions. Let's say that this beam started to fail, started to fracture due to bending stress. Where would that occur? At what point geometrically in the beam would that occur? It could be the bottom, but where on the bottom? In the middle, right? That's where the moment's high. So in the middle of the beam, at the bottom, it could be pulled apart. In the middle of the beam, at the top, it could be pushed together. We don't know whether this tensile strength, well, they did say it's tensile strength. We don't know if the tensile strength and the compressive strength would be the same. My guess is the tensile strength would be a little lower than the compressive strength, but I don't know for sure. Okay, so yeah, center of the beam at the bottom if it's failing due to this. What about if it's failing due to this? Where would that occur? At the ends, one of the ends, we don't know which one, but where at the ends? We already noticed that the maximum bending stress is at the bottom, but what about the shear? Well, that's maximum in the middle of the beam, right? So it'd be at the ends, but at the center of the cross section. Okay. Now here's another thing to think about. The shear stress that they've given us, I'm not 100% convinced that that's the lowest shear stress. I'll have to think about this a little more, but let's see. Let's go to the material properties and see if they have anything else. I'm curious. Yeah, go back to page 719. In fact, we haven't actually prepared it yet, so this will be good. Because looking at this, it looks like, well, it's definitely going to fail from bending because look how low that shear stress is. But remember, wood is not an isotropic material, right? It has different strengths in different directions. And so think with me for a moment. If we go to the end of the beam, so we don't need any of this anymore because we've got the stresses, assuming they're correct. I hope they're right. Okay. So here's the beam, and we're essentially looking at what's going on here. So let's take a cross section there. And this is where we're concerned about shear. So we're concerned about the shear stress at this section. Now, if we were to extract an element there, okay, a small, imagine just a small piece there, the shear on this face on the right would be like this. That would be the shear we're looking at here, because here we're just looking at it from this direction. Okay? Now, again, to keep this element in equilibrium, we have to have shear like that also, all the way around. Now, this shear, if you take a piece of wood and you try to shear it like this, it's not going to happen, right? I mean, at least not barehanded. If it does, I'm going to call you sir from now on, okay? Or very respectful, okay? Well, unless it's a toothpick, then I might not. Anyway, so we don't really expect this to be a problem. But what about this? Well, the grain of the wood runs this way. Well, the wood's not as strong in that direction, right? If you try to shear the wood this way, you could probably do it, right? In fact, let's say you wanted to make a seat for a chair, just a simple round seat. You're tired of all this engineering stuff, so you're going to just make a seat. And you cut down the tree and you see this piece that looks kind of like this. You decide to make a seat out of it. Is that a good idea? It's not as good of an idea as taking a piece that, let's see if I were to draw it more as an isometric, where the wood grain runs this way, right? That's going to be a lot stronger. Whereas this, you might be able, I mean, depending on how thick it is, you might be able to shear some of those rings off and fall to the ground, okay? So the point is that the strength is going to be very different depending on the orientation of the stress. And stress here is going to cause a lot more trouble than stress here. But these two are the same magnitude. My point is, this stress may be pretty important because it's causing stress in this direction. Remember the video experiment you guys are doing now? You're basically doing this, right? So you're working with a piece of wood, right? You just place layers on top of each other. It's kind of like wood. Of course, you've got less shear allowed between your layers. Wood does have some strength, some bonding between them. But it's the same idea. So even though this is a fairly low stress, we have to be really careful. So let's first of all compare. We'll go and look at the strengths of the wood. So let's see. Notice that the allowable stresses, they've got bending, they've got tension parallel to the grain, they've got horizontal shear, and they've got compression perpendicular parallel to the grain, and then the elastic modulus is the last part. So the first thing I'm going to do is calculate a factor of safety against this shear. Okay, so the factor of safety would be the shear strength divided by the shear stress. And notice they say this is the shear strength, this is horizontal shear. I think they're talking about this. Okay, taking the wood and shearing it, so applying a force this way and shearing parallel to the grain. Okay, it's the only number they give us, so we have to use it. Anyway, for number 2 southern pine, looks like that number is just 70 psi divided by then 39.2 psi. It's about 2 to 1, not quite a factor of safety of 2. In fact, what is the number?
1.79.
How much?
1.79.
Thank you. 1.79 is the factor of safety. But now let's go back to the bending stress. Now, do we want to use tensile stress? No, tensile would be just taking a piece of wood and pulling it apart, right? So we're not going to do that. Just like with the plastics, what we discovered before about the flexure strength, we'll use the bending strength that they have. Notice that the bending strength and the tensile strength are relatively close. They're not, obviously they're not the same. Some of them are about twice the other, but they're at least on the same order of magnitude, whereas the shear strength is an order of magnitude lower. Okay. Since we have bending in this case, that's the loading type we have, I think it's valid to use the bending strength of the wood. So the bending strength is 1,000 psi. So our factor of safety against bending then is 1,000 PSI divided by 737.15 PSI. Let's see, what do we get from that? 1,000 divided by 737.15 gives us 1.35 or so, well, 1.36 is the factor of safety. So the factor of safety against shear is higher than the factor of safety against bending, but they're a lot closer than you might have expected. I mean, when you first look at these numbers, you say, forget that, it doesn't matter, right? But in reality, because the strength of the material is so much less in that direction, well, then it's pretty important. It's pretty close in terms of how critical it is. Okay. What else could we do? Well, I noticed there's also compression perpendicular to the grain or parallel to the grain. Perpendicular to grain compression would be compression like this. Parallel to the grain would be compression like this. So we can also talk about what's going on at the top, because we know the moment at the center section is the highest, right? The moment there is the 13, 14 foot-pounds force. So since we've already figured out a factor of safety against bending at the bottom, now let's do that for compression at the top. Because the strength in compression is apparently different than the strength in tension. So let's see, parallel to the grain, number 2. Looks like the strength in compression is 550. Uh-oh, we have a problem. Compression versus tension. We've got 550 PSI as compared to 737.15 PSI. You can already see we have a factor of safety less than 1. So where's this thing going to break? At the top. It's going to fail right there, according to our calculations. Okay. Not much of a point in computing the factor of safety, but since it's up there, it's about 0.746. Not good enough, in other words. It's going to fail. Okay? Questions, comments? Kind of interesting problem. All right.